My apologies for that unplanned interruption. As I was saying, we're calculating the average. They want you to tell them what the resistance of the stove is. And in the previous question, you calculated RMS or VRMS. Okay. And there's a formula on your formula sheet that accommodates the average power as they've given you, the square of the VRMS, which you've just calculated, divided by resistance. Okay? So again, like I said, very important for you to have your formula sheet next to you, because if these are not things that you've looked at or seen recently, or it's going to be very difficult for your brain to know what's going on. Okay? So you substitute in 1600 watts as your average power. You put in the VRMS that you just calculated, which was 240.42 volts, and we square that divided by R. Now you plug this into your calculator, and the R that you get is 36.13 ohms. So this is the rounded off resistance of the stove that you have connected to the AC generator in question. Okay, now we just select and we move on to our final question. Question 11. So, you just give me a second. Perfect, okay. So, question 11.1. First it says, the threshold frequencies of cesium and potassium metals are given in the table below. So there's your threshold frequency. Obviously, you know that the symbol for threshold frequency is F0. Okay? So you say, we have a look at the first question. It says, define the term work function in words. Again, this is going to be on your definition sheet, and it goes as follows. Work function of a metal is the minimum energy needed to eject an electron from the metal surface. One more time. Work function of a metal is the minimum energy needed to eject an electron from the metal. Okay? Or from the metal surface. Okay? Also important, I know they haven't asked you for the definition, but threshold frequency, the formula is the minimum frequency needed for the photoelectric effect to be observed using a specific type of metal plate. Or in other words, the minimum frequency of light needed to eject electrons from the surface of a specific metal. Okay, so it's, remember, threshold frequency and work function are directly proportional. Okay, but we'll get into that now. The next question says, which one of the two metals in the table has the higher work function? Give a reason for your answer by referring to the information in the table. Okay, well, potassium has got the highest work function. Okay, the higher work function. And that's because, as I just said to you, threshold frequency and work function are directly proportional. And why can I say that? I can say that because work function, or work O, this is how you represent it, it's a W with a small little O at the bottom, equals H times FO. So work function equals a constant, our H constant, multiplied by our threshold frequency, which means that work function is directly proportional to threshold frequency, which means that as work function gets higher, so does frequency threshold. So the metal with the highest work function is potassium. because 5.55 times 10 to the 14 is bigger than 5.07 times 10 to the 14. Okay? Next, we have a look. It says the simplified diagram below shows two circuits, A and B, containing photocells. The photocell in circuit A contains a cesium metal plate, while the photocell in circuit B contains a potassium metal plate. Ultraviolet light with the same intensity and wavelength of 5.5 times 10 to the negative 7 meters is incident on the metal plate in each of the photocells, and the ammeter in circuit A registers a current. And it says 11.3, by means of calculation, determine whether the ammeter in circuit B will also register a current. Okay, so remember, the only way that we can tell if a circuit or if a current is being registered in the circuit is if the frequency of light that is being shone onto our metal plate is high enough to eject electrons, as in this metal plate will then let go of electrons and the electrons will be able to move around in the circuit. It's only if this frequency of light is high enough so that electrons can be ejected and move around in the circuit to register the flow of electricity or current through the circuit. So what they're actually asking us to do is to calculate whether the light that is being shone onto this metal plate has a high enough frequency for electrons to be emitted or ejected from the surface of the metal. Okay? And the way that we are going to calculate this is we have to see, is the frequency of light for potassium, is the frequency of light that's being shone on my potassium plate, is it higher, equal to, or lower my threshold frequency? If it's equal to or higher than my threshold frequency for potassium, then electrons are being ejected and there is current flowing through the circuit. If my frequency of light that is hitting this plate is lower than 5.55 times 10 to the 14 hertz, then no, there will be no current flowing through this circuit. Okay? But the problem is that they haven't given us the frequency of the light that's being shone on this plate. They've given us the wavelength. But that's not a problem, okay? Because we have a formula that can convert frequency or wavelength into frequency. And that formula is C, or speed of light, is equal to the frequency multiplied by the wavelength. Okay? And the speed of light is on your formula sheet. It's in the little summary on the first page of your formula sheet. So C, you can just substitute in is as 3 times 10 to the power of 8. This is the speed of light. We're working with light now, so we are using the speed of light. In Doppler, we were working with sound, so we were working with the speed of sound. So speed of light, like I said, this doesn't change. It's a constant that's on your formula sheet, is equal to, we are looking for the frequency of the light. We're trying to find out what is the frequency of the light that they're shining on this plate, right? They've given us the wavelength. So we substitute in 5.5 times 10 to the negative 7. Okay? Remember, we're trying to convert this wavelength into a frequency. So we substitute this into our calculator, and we are given a frequency of 5.45 times 10 to the 14 hertz. Remember, we're on question 11.3 now. Okay? So now we say, well, this is my threshold frequency for potassium. So this is the frequency of light that I need to be shone onto my potassium plate in order for electrons to leave the metal surface and travel through the circuit, and for electricity to be registered in the circuit. Okay? But the frequency of light that is actually shining on my plate is 5.45 times 10 to the 14 hertz. this number is smaller than this one. And remember, I said, if the frequency of the light was equal to or bigger than, then yes, electricity would be registered in the circuit. But the frequency of light that is being shone on my plate is actually less than my threshold frequency, which means that no. Okay, the ammeter in circuit B will show no reading. Okay, the ammeter in circuit B will show no reading. Why? Because the frequency of light that's actually being shone on my plate is not of a high enough frequency to allow electrons to be emitted. So you can see this is the frequency of the light. The threshold frequency for cesium is lower. So yes, there's definitely electricity running through my cesium circuit because my threshold frequency is lower than the frequency of the light that's actually being emitted on the plate. But for a different metal that has a higher threshold frequency, the frequency of light is not sufficient enough for electrons to be emitted off of this plate. Okay, next question. Let me just get rid of this. It says, calculate the maximum kinetic energy of an ejected electron in circuit A. So we don't have ejected electrons in circuit B, so we can't calculate it for circuit B. So we're doing it for A. Okay, again, if you go to your formula sheet, there's a pretty straightforward formula. Okay, and the formula for 11.4 goes as follows. Energy is equal to work function plus EK max. And EK max is what we're looking for. They want the maximum kinetic energy. So we say HF, remember H is a constant, F is frequency, is equal to our constant H multiplied by our threshold frequency plus half mv squared, mv max squared. Okay, now we go and we substitute in. Okay, this we can convert to hc over wavelength is equal to h times f plus half mv max squared. So you substitute things in. Your h, or your constant, is 6.63 times 10 to the power of negative 34 multiplied by 3 times 10 to the power of 8, which is the speed of light, over your wavelength, which is the wavelength that they gave you, 5.5 times 10 to the negative 7 equals my Planck's constant, or actually I'm not sure if it's called Planck's constant, but it's the constant for this scenario, 6.63 times 10 to the negative 34 multiplied by my threshold frequency, which is, my threshold frequency for cesium is 5.07 times 10 to the 14. 5.07 times 10 to the negative 14. Okay, remember, I'm just running out of space here, so this looks terrible now. And then plus our EK max. So you substitute all of that into your formula, and you should eventually come out with a final EK max. Once you've substituted all of this away and you've written it more nicely and neatly than I have, you get an EK max of 2.55 times 10 to the negative 20 joules. Okay, and that's the maximum kinetic energy with which these electrons are emitted from the surface of the metal plate. Okay, and then your last question says, how will the maximum kinetic energy of the ejected electron calculated in question 11.4 change when the intensity of the incident light increases? So you're choosing from increase, decrease, or remains the same. And the answer is, if you are increasing the intensity of the incident light, your EK max is going to remain the same. It's not going to change. Okay? Increasing light intensity increases the number of electrons that are ejected. It doesn't increase the EK max. Okay? So increase light intensity equals more electrons ejected. Okay, increasing the light intensity. So you're not changing the frequency, you're changing the intensity. You're changing how bright it is, how intense it is. Okay, that's going to mean more electrons are ejected from the surface of the metal. But they're not asking about number of electrons, they're asking about the kinetic energy of the ejected electrons. And the only way for you to increase the energy of the ejected electrons is to increase the frequency of your incident light. Not the intensity, the frequency. Intensity means I'm making it brighter. Frequency means that I'm changing the nature of the light altogether. So if you want to change your EK max, you need to increase the frequency of the incident light, not increase the intensity. So how is maximum kinetic energy affected by an increase in intensity of incident light? The answer is, it's not. It remains the same. Okay, cool. Thank you for watching.